Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. So in this live stream we're gonna explore a new technology, or should I say not really a new library, but like a new library version. It's of course SDL3. Now SDL3 comes with like SDL GPU, which is basically a middle ground between, at least in my opinion, a middle ground between Vulkan and something like OpenGL. There was always a need for such a rendering interface that is not as hard and complicated as Vulkan and not as, not as bad as OpenGL, right? So SDL3 GPU, I think, would really fill a huge gap in the graphics programming ecosystem. And Loop Preliminary, welcome to the live stream, as always. Thank you for tuning in every live stream. So yeah, all right. So where do we even start? Let's see. Is the stream, by the way, good? Is my voice good and everything? Because I just set up this thing right now. Let me know. Okay. Let's get going. I haven't used SDL3 GPU a lot. So far I just made a triangle with it, right? And there isn't a lot of videos out there and learning, like there's no learning resources and no videos about it right now. There's only the official examples. But hopefully today we're gonna be the first ones to kind of try on YouTube, especially even live together. All right, so let's get going. Okay, so the first thing first we're gonna need is to set up. Oh, by the way, let me grab my chat real quick. Hold on, pop out the chat. All right, let's go. All right, the chat is perfect. If you have any questions, please let me know. All right, let's get going. All right, so the first thing that I'm gonna go for is, I made before a video about Modern CMake. You could check this out. You can check out this repo right here. You're probably gonna find the link down in the description below. And I'm just gonna copy this CMake list. Of course, I'm gonna actually create a new project, right? Hopefully we can, make a freaking game engine, but we'll see about that. Anyways, of course we're gonna be using the latest modern, C++ stuff, because I'm crazy, but whatever. Anyways, so let's call it Kodachaku Game Engine, because I don't know any more creative name for now. So Kodachaku Game Engine. Alright, perfect, and let's just create this thing. Alright. And somehow in Morocco, even if you like start a live stream at midnight, there's always some sort of motorcycle ruining the experience, but whatever. Anyways, yes. Alright, they just basically spawned. Whatever, alright. So let's go to settings. You could use whichever IDE as long as it supports CMake, but I'm using C-Line here. Okay, let's go to, well, first of all, CMake. Here I'm gonna go with the build directory build. And of course I'm gonna use Visual Studio, basically MSVC. I'm gonna use Ninja for the generator and apply. Okay, I don't need this thing anymore, and let's go. All right, perfect. Now if we try run this, we're gonna get our famous hello world program. Perfect, cool. Now let's just do some copy pasting from if you want to understand more about this code, you can check out my latest video on my channel. I try to explain all this stuff. So you're basically gonna copy this part. We're gonna remove some stuff though, but we'll see about that. So I'm just gonna like copy this whole thing, really, and I'm gonna come here and then gonna do this, right? I'm gonna paste that stuff in. I'm gonna remove this, I don't need it. And then I'm also gonna remove this, really. I'm gonna make a src directory here. And then I'm gonna put my main.cpp there, refactor. Alright, I don't think I'm gonna use mgui, at least probably not in this video. I think. So we could just remove it for now. I'm gonna use SDL, of course. SDL image, probably, I guess. Flex and SQLite, of course not. If we want them later on, we could just, you know, get them back, right? Copy them back. Alright, so that's basically it. Add executable. Instead of demo, we're just gonna call this, I don't know, engine. src main.cpp. And there you go. So let's just refresh the CMake. And now it's gonna go ahead and this code will basically download all the libraries, set them up and do everything for us. Right now we could just have a coffee or something, but I already got my coffee, so I just gotta wait here. But yeah, alright. Let's see. So right now it's running the SDL CMake stuff. Pretty much. If you guys have any questions, please let me know. So we're gonna be following with SDL examples. SDL3 GPU examples. These are the only learning resources for now. There is another resource. I'm not sure where I've seen it though. Moon something. Yeah, there we go. It's right here. This blog have some information. Basically, this blog is from someone. Well, I'm just gonna put the link here. From someone who helped in making SDL GPU, and is actually one of the, like, this blog post especially will have the background. So he especially worked on, I think, FNA, right? Yeah, the FNA project. He's a co-maintainer of the FNA project, and he also worked on the SDL GPU. So you could check out this blog post. It's quite interesting. There's some interesting insights there. But yeah, all right. Let's go back to the examples here. There we go. And let's go. We have examples. And the first thing first, of course, is we're gonna need clear screen.c. So it's basically just 50 lines of code. Of course, though, without the common code. It's basically a little abstraction here to make it easier to make examples, which is right here, this code. But no worries, we're gonna do everything in line. So you could understand it easily, and hopefully I'm gonna try to explain everything as I go, pretty much. That's basically it. Alright, so let's just wait for this to finish. The configuring is done. I think right now I could just like run this thing so we can build the libraries, and then of course it would build our executable. There we go, it's building SDL right now. The other nice thing about this approach of using CMake, or at least Modern CMake, well, what the heck, hold on a second. No work to do, that's strange. Oh, the wrong target. Okay, hold on a second. Let's go with this one. Or honestly, let's just call it so it doesn't get confused. Let's just use the project name, because apparently it did get confused here. So let me just use the project name so that doesn't happen to someone else. Hopefully it wouldn't take too long to reconfigure. Yeah. At least you wouldn't like re-download everything. There we go, it's done. Now let's build that thing. Alright. Now it's building SDL image. As I said, the nice thing about building everything from source is that when some problem happens, you can actually jump into the source code of SDL and see what the heck is going wrong, or whichever other library. But yeah, so SDL right now is set up. So right now we could actually start working on the thing. Alright, so of course we're gonna get SDL.h pretty much. And now we can say SDL init. And here we're gonna say SDL init video, so we could initialize the SDL video subsystem, because there is, well, multiple subsystems. There is, if you hold control and click on that, there's audio, video, joystick, haptic, gamepad, event, sensor, and camera. So we only need video for now at least, so we're gonna go with that. Of course, if you actually see the documentation of this guy, you could find some more information, like what it returns. Hold on. So true on success or false on failure. Call SDL get error for more information. Alright, so whenever there is an error, I'm just gonna make an SDL exception class, and I'm also gonna be using a bit of GitHub Copilot to help me here do stuff real quick. Well, not really that. Runtime error. There we go. It's just gonna do its thing, nothing fancy. And oh, let me activate the save actions on save, so it would reformat code automatically when I save it. And here, let's make this final. Why not? Let's make this explicit. And here we're basically initializing the base class of runtime error with the message. Though we're also gonna add plus, like a new line, plus SDL get error. Okay, so a custom message from the user of what the error that happened plus the actual SDL error. Perfect. Now what we're gonna do is, if true on success, so, and false on failure. So if not SDL init, then we're gonna throw an SDL exception, SDL init failed. Alright, let's make sure that this is actually working first of all. And it does work, perfect. Now let's create a little window. So SDL create, well, of course this should be a pointer. Yep, and SDL create window. Alright, so here we got the title of the window. Let's just say Kodachaku game engine, I guess. The width, let's just go with 800, 600 for now for the height. And then here we're gonna go with SDL window hidden. So we could actually show it later on after we make sure that everything is ready to be displayed, because like the device creation takes some time, so we don't want to show the window black or with some indefined data. So yeah, SDL window resizable, so to make it resizable, and there we go, we got a window. So SDL create window, if you check its documentation, this is all the stuff that is possible that you can like add to the flags. But other than that, if you come down here, the window that was created are null on failure. So here again we're gonna say, if not window, then throw SDL exception. We could, no, actually no, don't do that. Perfect. Why the heck this syntax color stuff? Okay, it's fixed now. Perfect. Next up, we're gonna need an SDL device. GPU device. This is the new API of SDL to create rendering stuff. So here we're gonna have a device. So SDL create GPU device, and let's see what we got here. So this creates a GPU context. Format flags. So first, a bit flag indicating which shader formats the app is able to provide. Now, SDL GPU can run on multiple platforms. It can run on Mac OS, Windows, Linux, you name it. There's a lot of supported platforms. I think even Android maybe. So I don't think console just yet, I'm not sure. But either way, we're gonna need to tell it which GPU shader formats we're gonna be using, or we're gonna be providing. So in our case, we're gonna be providing everything. Like we're gonna be providing SPIR-V for the platforms that uses Vulkan. We're gonna be providing MSL for the platforms that uses Metal, like Apple hardware. And finally, SDL GPU shader format, DXIL for the platform that uses DirectX, like Windows and Xbox. Okay, perfect. What is the next thing? So the debug mode. Enable debug mode properties and validations or not. Since we're debugging right now, we're just gonna go with true for now. And the last thing that we have here is the name, the preferred GPU driver or null to let SDL pick the optimal driver. Okay, so we're just gonna let SDL pick the optimal driver for us. So null PTR, perfect. Now we're gonna say if not device, then honestly, let's give this some more better messages, I guess. SDL initialization failed. Couldn't create window. Yeah, let's do the same thing here. Couldn't initialize SDL, perfect. And here, same thing, couldn't create GPU device, perfect. Alright, so now we gotta actually make this device own this window. So we're gonna do it using SDL GPU own, I think. I don't remember the name exactly, actually. Own. Well, we could check out the examples here. So claim window for GPU device. Okay. So SDL claim window for GPU device. So here we give it the device that we created, and we give it the window that we want to claim. So of course, of creating a swap chain structure for it. If you know Vulkan, then this makes total sense. But you don't really have to know Vulkan to make use of this. Alright, so claims a window, creating a swap chain structure for it. This must be called before SDL acquire GPU swap chain texture. It is called using the window. You should only call this function from the thread that created the window. You could also set up the swap chain, vsync and like parameters like that using another function called set GPU swap chain parameters, though we don't need it for now. So true on success or false on failure. Perfect. So if not SDL claim window for GPU device, then we're gonna throw, let's leave the AI do its job here. Couldn't claim window for GPU device. Perfect. Alright, and finally, when we're actually done with this process, we can actually show the window. We're ready to show the window. So there we go. Alright, so now if we actually run this, if everything goes well, we should be able to see a window pop up, but then it would close immediately because we don't have an event loop yet, which would keep the window on, or our application on, because after we show the window, it just returns 0. Or should I say exit success, which basically we're gonna exit the program here, which is not great. Okay, so while so of course we're gonna need a bool is running, or let's actually go with bool is running true, and we're gonna say while while it's running. And of course we need an SDL event. We could just put it here, I think. I hate the fact that the coloring gets messed up here for whatever reason. Kinda annoying, but anyways. So here, while it's running, so this is like the game engine loop, or like the main loop, right? And this is of course the event loop, right? So we're gonna basically pull the events, every event, and then we're basically gonna process it. Alright, so here we're gonna switch on which event we got. So events.type. Now if we got an SDL event quit, then we're basically gonna turn is running to false, which means that when we actually go to the next iteration of the while loop, it's gonna quit this loop to the program exit, right? So we can exit the application. This event is basically emitted when you try to close the window, for example. Though if you had multiple windows, you do need some extra logic, honestly, to make sure that this is working properly. But for now, we only have windows, so it's fine. Alright, so with that out of the way, we could also generate a default statement to silence that warning. And function main always returns 0. Okay, let's go right now and run this. And there we go, we got our resizable window, though it doesn't really have anything in it, of course. So now we gotta actually go into the actual SDL GPU stuff, right? So basically here we created a window. So here we initialized SDL. Here we created a window. And here we created a GPU device. Well, we didn't create an actual GPU, of course, that's not possible, but like in some sense it's a logical device, right? And in fact we could see more description maybe on this. Let's see, there isn't that much of a description there. What about here? Oh, checks for GPU runtime support. That's interesting. Get GPU shader formats, GPU device driver, destroy GPU device, GPU support shader formats. Alright, whichever, anyways. So GPU logical device, and then of course, well, we attach or claim window for GPU device, then we show the window. And finally we get into the main loop. And yeah, that's basically it. Now let's go to the next step really. So we're done with this part. Comment quit. Let's go to clear screen here. So the next part is we need to actually acquire a GPU command buffer. So basically in the regular APIs, like let's say OpenGL or like the old SDL rendering API, is that like when you run stuff, like you just call functions and things happen, like. But here in the newer or modern APIs, you actually create like a list, which is called the command buffer. And then basically you keep on adding to that buffer or that list commands, and then you send them to the GPU at once to be executed. And when you actually send them, you don't wait for the GPU to finish. You just send it and you forget about it, right? And so this is useful for parallelism, meaning like you could create multiple threads and every thread would generate like a different command buffer or command list, and then you can submit them all to the GPU to be ran by the GPU. But anyway, enough talking, let's go into business here. So after the event loop, we could like grab a GPU. Wa alaikum assalam, Robert. Welcome to the live stream. How's it going, mate? Welcome back. SDL GPU command buffer. Okay. I'm not sure how I can change the naming conventions of the IDE here, but whatever. So SDL GPU, or should I say probably acquire, yeah. Acquire GPU command buffer, there we go. So here we just give it the device. Is this just easier than Vulkan? Yeah, way easier. You don't have to, it's basically Vulkan, but without those messy details that no one really, like, at least most people doesn't care about, like synchronization and stuff like that. It's all automated or hidden, basically. So it's like Vulkan, but simplified down, essentially. But yeah, if you have any other questions, please let me know. Do you have to make all your own shaders, or do you get all that stuff for free like in OpenGL? You basically, for SDL GPU, you just give it the shader binaries. You give it the SPRV, like for Vulkan backend, you give it the MSL for metal, and then you give it the DXIL, like the HLSL shader binaries for DX12, like for DirectX 12, right? But yeah, or you could just remove those, and like, let's say this ran in Apple, which of course doesn't have a Vulkan backend, or at least probably doesn't, right? So what's gonna happen is that this function would probably fail. Yeah, pretty much. Okay, so what this does, a command buffer or null on failure. Okay, sure. And of course, this command buffer is managed by the implementation and should not be freed by the user. The command buffer may only be used on the thread it was acquired on. The command buffer should be submitted on the thread it was acquired on. Okay, perfect. Now I could basically record multiple commands into this command buffer. I think everything works everywhere except OpenGL iOS. It got deprecated or something. I don't know, and I don't think OpenGL is implemented as a backend in SDL GPU. I don't think so. Probably not. No. I don't think so. You only give the binaries of SPRV, MSL, and DXIL. You don't even give the source code. How do you get those binaries? There is multiple ways. It's your own business. You could either do offline shader compilation, or you could do online shader compilation using some library. For today, or at least for now, we're probably gonna go with offline compilation shaders. And honestly, for now, I'm not gonna do the compilation myself. I'm just gonna grab the examples here, the content folder here, so we could keep things very simple, at least until, you know, until we get the basics down, right? Anyways, so after we acquire the GPU command buffer, then we have to acquire a GPU swap chain texture, which is basically one frame, which we could draw into. Right, so let's see. SDL GPU swap chain. Well, it's just texture, I think, yeah. And then swap chain texture. SDL acquire GPU texture, I think. Wait and acquire GPU swap chain texture. Okay, interesting. Alright, so here it basically blocks the thread until swap chain texture is available to be acquired, and then acquires it. Gotta try this later. Yeah, it's pretty interesting. Command buffer, and I haven't used SDL3 yet. I've used it just today, pretty much, and right now I'm just recreating the triangle that I made, and hopefully we could do more in this live stream than the triangle I made, but we'll see. Alright, so we gotta give it the window, and then finally we gotta get the swap chain texture, a pointer filled in with a swap chain texture handle. Okay, sure. Oh well, it doesn't work that way apparently. I need to grab this and do something like this, something like that. Is there any other parameters that I need here? Yeah, the swap chain texture width, a pointer filled in with the swap chain texture width, maybe null. Okay, give it null PTR. I would assume it would just basically infer it from the swap chain size. And yeah, that's basically it. Now, when a swap chain texture is acquired on the command buffer, it will automatically be submitted for presentation when the command buffer is submitted. The swap chain texture should only be referenced by the command buffer. Used to acquire is an error to call. Okay, interesting. So we gotta basically make sure that the swap chain texture is valid, because it could be invalid, like it could be null if the window is minimized, for example. So if we do indeed got a swap chain texture this frame, what are we gonna do with it? Well, we're gonna start rendering using a render pass. So let's go. SDL GPU render pass. Render pass. Create GPU render. Well, not create apparently, it's begin. Okay. Begin GPU render pass. So this needs a command buffer. So we're gonna use the command buffer that we required in this frame, and it requires an array of color target infos. Of course, this is a C API, so we gotta give it a pointer and a number separately in separate parameters. And then hopefully the depth stencil target info. Okay. So color targets. Alright. So since we are in C++, we could just make a vector color targets. Of course, we gotta need to include that vector thing. I honestly prefer C-libs. They build so much quicker. Yeah, true. SDL. So what this takes? This takes an SDL GPU color target info. Okay. GPU color target info. I would have made classes and stuff like that, you know, RAI to simplify things. Well, not simplify things, but like make things more C++-y, I guess. But for now, I'd rather not, just to keep things very simple for new people and even myself right now, because we're still learning. So things would be very linear, no crazy, you know, jumping all around the world. So yeah, color targets. And here we're gonna have one color target for now. And for that, we're gonna go with SDL GPU color target info, color target. And here, is there like some information about this? Doesn't seem like it. But anyways, we gotta give it the texture that we want to draw into here, which is our swap chain texture, of course. And what else? Color target dot. There is quite a lot of stuff here, apparently. We need the store OP, SDL GPU, store OP, store result, don't care. Just set this to store. If we need MSAA later on, we're gonna need resolve. I understand this stuff because I'm coming from a Vulkan, you know, Vulkan background, but you don't really need to really care about this stuff right now. Just that it's a store. They actually wrote don't care. Yeah. So like if you do don't care there, it would basically do nothing to the frame. It wouldn't write anything. And since here, well, hold on a second. Yeah. Anyways, whatever. Let's go to the next thing, which is Lloyd OP. Yeah, so basically this is the first operation that, well, this is the first operation that we're gonna do to the frame, or to the, should I say the attachment, which is our swap chain texture. And this is the last operation that we're gonna do. The last operation is that we're gonna keep, or we want to keep, the data we wrote to the swap chain texture. And the first operation that we want to do is to clear this thing, is to clear this attachment using a specific color. Alright, so you could say don't care, and then it wouldn't really clear it. I don't think you want that. Anyways, what else? We also need to give it the clear color, since we're using a Lloyd OP clear here. So color target dot clear color. Okay, now here we're gonna need an SDL F color. Of course, we're gonna need the red, green, and blue. Let's go with a red color, because why not? Red is cool. Perfect. And now what we need. Oh well, make sure to initialize this, otherwise it would have garbage values. And since we're initializing the vector with one item, we could just omit that. It would be inferred. Alpha needs to be, oh yeah, true. Alpha needs to be 1f. I don't know if I did 0f. It may be transparent, though I'm probably gonna need to add some extra property first if I want that. I don't think a lot of people need that anyways. Oh, well, I still haven't continued the render pass stuff. Alright, so we got the command buffer, then we got the color targets.data. So basically we get the C pointer to the vector, or to the array, or whichever you want to call that. And then the size here, well, color targets.size. For the length or the number of the color targets. And finally the depth stencil target info, a texture sub resource with corresponding clear value and Lloyd store OPs, maybe null. For now we don't need depth because we're not into 3D stuff just yet, but later on we may need that indeed. And there we go. So okay, what this returns? A render pass handle. So I guess it cannot fail then, right? I would guess so. And of course, anything that you begin, you should end. So SDL and GPU render pass. Render pass. You don't have to understand all the stuff that I'm writing here just yet. You'll understand everything as you go. Just try to, go with the flow for now until we get into it, basically. And if you guys have any questions, please let me know. Alright, we're not having any red color. Oh yeah, because we're not submitting this command buffer to the GPU just yet. Yes, we're recording this render pass into it, render pass commands, which is the begin, render pass, and end, but we're not really submitting it. So the last step here is to submit it. So SDL submit GPU command buffer to the GPU. Gonna give it the command buffer that we want to submit, and so submits the command buffer to the buffer so its commands can be processed on the GPU. It is invalid to use the command buffer after this is called. This must be called from the thread the command buffer was acquired on. All commands in submission are guaranteed to begin executing before any command is subsequent submission begins executing. All right. True on success, false on failure. Okay. So we could again say if not that, well, if not, it is one command buffer per frame, or can you have 10 of them? Yeah, you can make, though there isn't, well, you could make multiple command buffers per thread, to make things way faster. Now, there is quite, this is comparable to Web GPU. The problem with Web GPU is that it doesn't have a lot of threading capabilities. It only uses one queue, though I'm not sure you may be able to record command buffers in multiple threads. I don't think you can in Web GPU, but SDL it does have multiple queues. It does use multiple queues, I think. No, I'm not sure. We're gonna find out, I guess, with time. Anyways. Couldn't submit GPU command buffer. Alright, perfect. Perfect. I'd rather use this instead. Why not? It's gonna take me a little while to actually. Nothing really important. I should have probably not wasted time on this one. Anyways, whatever. Alright, perfect. I think we're good now. Swap chain texture. Yeah, perfect. Alright, let's try this out now. See what happens. And yeah, we got our screen cleared. Perfect. I'm not sure which backend is being used, by the way. I wonder how to actually know about that. Got to use that feature, can't go without a brace. Yeah. Alright, let's see if I can figure that out. I'm not sure. Get GPU driver. Get the name of a built-in GPU driver. Okay, I think this one probably. Alrighty. So, but this one, let's see. I think we do have print, right? In C++. In modern C++ at least. Huh, let me see. Yeah, there we go. Perfect. So std print. There we go. Well, we could actually do it after we create a device. Alright, let's see. Vulkan. Alright, perfect. Vulkan. Interestingly, maybe it doesn't add. Oh, there is print line. Okay. Without ln, it doesn't add a new line. That's why. Alright, so using GPU device driver Vulkan. So in my case, it used Vulkan basically. Yeah. Alright, what's next? So we cleared the screen. Now we need to show a triangle, a basic triangle. Now this is where things start to get hairy. Really hairy, because like the shaders, you have to give the shaders in like multiple formats, basically depending on the backend that is used by SDL on the current platform. So things start to get a little bit crazy here. So we have this Lloyd shader function right here, right? And this one is not really part of SDL. It is part of the common file here that is used as a utility file, kind of. And if we come here, you know, we could actually just copy this whole function and call it a day. And don't bother with it too much. You know, just copy that, paste it here, so we don't go crazy. Though this is not really compatible with C++, we have to change some stuff. Alright, so first of all, we auto detect the shader stage. So first of all, this takes a device, a shader file name, a sampler count, uniform buffer count, storage buffer count, and storage texture count. Alright, so we could make this into a std string in a second, but for now, let's just make use of null ptr first of all. On all of these, I could just say more actions. Don't think of it as copying, it's borrowing. That's a funny comment, honestly. Replace zero value pointer with null pointer function. Load shader. So I'm gonna replace all that nulls into null ptr in this function. And what's next? We also have this guy right here. I'm just gonna comment it out. I'm gonna let the AI convert this into valid C++ code pretty much. There we go. Perfect. Good boy. Let's go. Or good girl. I'm not sure if the AI is a girl or boy, but whichever. Alright, so here, more actions. Static cast. Walaikum assalam. Whoa, G Gearing. Welcome back to the live stream. Alright. Perfect. Perfect, perfect, perfect. So we could remove this now. Alright, so what's next? Now we're also gonna need this content. Now it doesn't really have to be content, it could be our own shaders stuff, but for now, to keep things very simple, I think that syntax.field is valid from C++20. I don't think so. I mean, it wasn't working at all, pretty much. Okay, what I'm gonna do here? Yeah, so here's the deal. I'm gonna go ahead and like deploy the zip file or folder of this. Right? I already deployed it, but I'm gonna do it again just for the sake of showing you how. Variable code wasn't defined. Yeah. So I'm gonna basically copy this content folder as it is. I'm gonna paste it in my own project. So I'm gonna, well, where is that thing? Oh my god. Open in Explorer. And I'm gonna paste it here. I'm not gonna change anything. It basically contains some compiled shaders in the format DXIL for DirectX, MSL for metal, and SPIR-V for the Vulkan backend. And of course the source all in HLSL with a compile.sh script which uses a shader cross, well, an SDL shader cross or translator. I don't remember what it's called. I mean, hold on, let me see here. Hold on. Shaders source compile.sh. There we go. Yeah, it's called shader cross. It's using this tool to basically take those HLSL files and it's translating them into SPV, MSL, and DXIL. So that's perfect. Would you like to install shell verify? I mean, why not? And can we actually? I don't think we can run this. I don't have that. Git for Windows. That's interesting. Let's try this. I'm not sure what happened there. Command not found. Shader cross, yeah. I haven't actually tried this yet, but we could check it out. Like SDL GPU shader cross. So this is the thing that we need. Shader translation library for SDL GPU API. Though there's probably like a binary though. This one is like the library is for online compilation of shaders. SDL shader tools. That's strange. Okay, so SDL shader tools. Let me paste this here. And let's see. No, this is another project apparently. Yeah, I do remember. So like SDL also made their own language that they're working on right now, or their own shader language. But we're not using that here. I'm not sure. Shader cross. That's very interesting. Is there like a release here or something? This is weird. Or is it just the Vulkan SDK shader cross that I know? I mean, let's try to actually do that. Why not? Let's download the Vulkan SDK real quick here. SDK. I mean, it would be useful to debug my stuff anyways to see what SDL is exactly doing behind the scenes. Installer. Let's go. Either way, I don't really need this stuff right now. We could just continue on the example actually. So, alright, let's go back for now. Alright, so we have this add const, sure. And I think we're done with that one. We could make this more modern using C++, but for now, let's just ignore that. Add const in file. Okay, sure. So now we have this load shader function. Perfect. Let's actually use it. So before we show the window, we want to create our shaders. So SDL shader Lloyd shader. So we gotta give it the device and then a shader file name. Okay, let's grab that from the example. Where's the example? Examples. And let me go back, by the way, to the, I think it got downloaded. There we go. Let's actually install the Vulkan SDK. And here, let's go to basic triangle C. Perfect. Okay, let's see what we got here. So we raw triangle.vert. Raw triangle.vert, yes. Raw triangle.vert. And the others, the storage buffer count and all that other stuff, we're just gonna go with zeros for now. Colloid the vertex shader. Well, this is the vertex shader SDL. What the heck is it called? Hold on. SDL GPU shader. Okay. There we go. Perfect. So if not the vertex shader, then do that. Alright, now the next thing is the GPU shader. For the GPU shader, it's solid color.frag. That's what it's called. Alright. Now, if not fragment shader, then throw an error or exception. Alright, perfect. Now let's see if we have that shader cross thing here. We don't. That's interesting. But I guess we'll find out later on. Anyways, why does this go back to main.cpp? Alright, perfect. So now we got a vertex shader and a fragment shader. Now we need to create a pipeline pretty much. So to create a pipeline, well, let me actually explain what the heck is happening in that Lloyd shader function first of all. Why not? Alright, so here we got a GPU shader stage. So here we're trying to search the shader file name and see if it have vertex.vert here. This is just basically for convenience of auto-detecting the shader stage. So if there is .vert in the name of the file, then of course it's a vertex shader. Otherwise it's a fragment if there is .frag in the name. Otherwise invalid shader stage. Well, here we're actually gonna use, instead of this, let's throw an exception and recognize shader state. Well, not an SDL exception. It's more of a runtime exception, runtime error. There we go. Now, full path, backend formats. So here we're getting the backend, turn the supported shader formats for this GPU context. So of course, like if it's using the Vulkan runtime, or should I say the Vulkan backend, then it's gonna give us back the SPIR-V backend format here. I see, but why it's giving 1? It's, yeah. Oh, it's a bit flag, I see. All right, fine. So I guess maybe it could be multiple then. Interesting. So here we're starting with the invalid format, and then we have an entry point string. Then so if the backend format's bit set contains shader format SPIR-V, then we basically construct a path here, content shaders / compile / SPIR-V / the name.spv. And here we have a base path. Oh yeah. The base path is interesting. To set up that, let's see. Should be somewhere around here though. Well, it's not here, it's in the common file, yeah. So there we go. GLSLC appears to be the name of the Vulkan shader compiler. Interesting, but why they're calling it Well, we'll see about that later on. Anyways, right now we don't really need it, so it's fine. And here, let's just do this, and there we go. Okay, so initialize asset loader base path is equal to SDL get base path. Get the directory where the application was run from. SDL caches the result of this call internally, but the first call to this function is not necessarily fast, so plan accordingly. Alrighty. So of course we gotta make sure to initialize the asset loader so we can initialize our base path here. So after we initialize SDL, it may be possible before even initialize it, I'm not sure. But let's just do it here. Initialize asset loader. And yeah, that's basically it, I think. Right now it should be good to go, I would guess. Let's try this out. Though we're gonna have a little problem though there. We're gonna have a little problem. There we go. So we got an exception, as you can see. And this exception is coming from main.cpp line 115. Couldn't load vertex shader. Couldn't load vertex shader. Why that's the case? Because it couldn't actually find the path. Though, hold on a second. If we actually even check the console, failed to load shader from disk, and then it gives us the file name here. Though I would rather actually just throw here instead, really. So like if not shader, then just freaking throw an error here. Well, couldn't create. Yep, okay, fine. Now if we actually do this, failed to load shader from disk. It's still actually thrown here instead, which is interesting. Yeah, we could easily fix that in CMake itself by basically copying the assets. So file copy, assets, destination, CMake runtime output directory. Now there is one little problem with this, is that this would only work on the generation of the CMake file. So like if you change the content directory, it wouldn't, you know, update unless if you regenerate the CMake, which sucks, but for now it would work until we have a better solution, or at least until we find a better solution. There's those like custom target stuff, but I didn't get to make it work just yet. But for now, this should work, I think. We probably need to add /bin there though. And not assets here, this should be content. Content and the destination CMake runtime output directory, probably /bin. Because that's where I'm putting my stuff here. And let's regenerate the CMake and run. So this would go ahead and like copy the folder, hopefully. Failed to load shader from disk. What? Build bin. Really? That's interesting. That's really interesting. I'm pretty sure this worked for me before. What I'm missing. Yeah, I mean, it's right here. Oh, never mind. We don't actually need this bin. Apparently, so let's regenerate this and let's try again. It should work now, I think. There we go, it's actually copied it over, and right now we're actually loading the shaders successfully, which is perfect. Though, as I said, we do need to find some better solution later on, but for now this should work. Alright, what's next? So we create the shaders, and in fact we also gotta release the shaders later on after we create the pipeline, because we're not gonna need them. And release GPU shader, there we go. Vertex shader and the fragment shader. Now what the heck is going on here? Oh yeah, we probably gonna need the device first. There we go, and yeah, cool. Now before releasing these shaders, we gotta use them in creating a pipeline. So for that, let's go back to our basic triangle example here. Let's see what we got. By the way, we could actually work more on this function. In fact, let me show you some things. First of all, this SDL ascend printf, it's super ugly. We could actually make full path being a string, full path, and then we could just comment this out and let the AI try to do this thing. Let's see, base path. Now apparently this should be instead an std string. That would be great. Static const. Yeah, that would be great. And So we remove the const there, and there we go. So we got that, perfect. I think we could also use this, no? Apparently it doesn't seem to work for whichever reason, but we could just use plus anyways. Though honestly, instead of using this, I'd rather use the std format, really. Yeah, let's use std format instead. Isn't that a nim thing? I do remember someone using it. I think maybe C#. It's probably even in C++. I'm just not sure why it didn't work there. But anyways, so here we got some placeholder, and we got a placeholder here. Here we give it the base path, and then here the shader file name. Perfect. Well, same thing with this one. I'm just gonna comment it out and let the AI do its job. Comment this one out and let the AI do its job. And there we go, done. Now we don't need these anymore. This is way cleaner now. Perfect. Now Lloyd file full path. Let's just, for this one we could actually use C++ files stuff. And for that I'm just gonna do this. So std. Well, first of all, let's grab, we need a vector of uint8 for the code. And then we gotta use an std, what is it called? iStream, I think? Yeah, file full path. So, of course, let's include the file that is needed for that one, which is basically, what is it called? iStream, yeah. Yeah, there we go, it's binary. And also another thing is that we want to actually like advance to the end of the file so we can get the size of the file. Now here, what's up? Full path cannot convert. What? So what full path is first? It's a std string. So why it's not wanting to? Oh, fstream probably, not iStream, my bad. So include fstream though, not iStream. There we go. Perfect. Now the next thing is we gotta check if not file. Then we gotta basically throw a runtime error. You can too, I believe, std string contents. Let's not go into that sorcery for now. Iterators can be quite tricky, though we could probably make use of AI here. Let's see. Nah. Let's just do it the regular way for now, at least. We could try to search that up later. Okay, so if not file, then we couldn't open the shader file. Perfect. Now let's get the size basically. So code.resize file.tellg. Tellg basically tells you like the current offset in the file, and since we have advanced to the end of the file, then this would be the size of the file. And then of course we stick g back to 0, so like we go back to the beginning of the file so we can read it right now. And finally we read the data from the start of the file, giving it the code size. And let's just static cast this so we don't have that warning to std stream size. And yeah, that's basically it. And now we don't need the static cast anymore, maybe? Or what exactly? Well, actually, first of all, we do need code.cster, I think, or data, yeah, my bad. Yeah, there we go, cool. Lovely, so just get a pointer to that vector of bytes. And that should probably work just fine, unless if I missed something. Oh yeah, I see. So code.size here. Oh yeah, we don't need SDL free stuff here anymore. And that's perfect. Let's go. And there we go. So right now we're actually using the C++ version, which is cool. What's next? We could ask the AI and see if it can make that work. I'm just gonna give it that thing that you said and see what it's gonna say. I did see that before. This is so much less than just using vocal. Yeah, for sure. A lot. The code reads the entire file into a std string and it converts. Let's see if this crap is working. Okay, I'm just gonna calm this out for a second. So of course the same thing. Here we got this std string, string buff, iterator, remove redundant. What is that last? Interesting. Okay, let's see if this works. I mean, it seems fine, I guess. So yeah, this is probably more. Hold on. Though we're creating a string, then we're creating that. Oh, can't we just create like a vector directly? We're creating a string and a vector. Can you create the vector directly? Certainly. Yeah, we just had like an extra string for no reason. And there we go. Perfect. We don't need this redundant template argument. And that should do the trick. It's that simple, man. Oh my god, that's nice. It's nice. Perfect. Now let's actually throw here instead. That's the C++ 17 thing. Yeah, template deduction, true. No support shader formats available. And yeah, that's basically it. Using all those features. Yep. Is there anything else I could change? Oh yeah, the SDL CR here. We could change that too to std find. Well, I don't think that's how it's supposed to be like. Well, you know what? Let's not waste too much time and just ask the AI directly, really. Use std find. And though there is ranges now. std ranges find instead of begin and end, right? So it's not I see. I forgot about that. So we could just make this a string. Now usually I would actually say string view, would use string view, but since this is supposed to be a C string, which we should make sure that it's like that it have like a C null terminator, I'd rather go with a string instead. So I'm just gonna say string const string shader file name. And of course I gotta include string.h. Whoops. Right. Oh yeah, wait, string view isn't guaranteed to be exactly, yeah. It could be just like a portion of a string. That's why I usually, for this case, I use a string, basically. And what the heck is going on here? Hold on. Namespace string. Okay, there we go. Shader file name. And of course, I'm just gonna get a reference. I don't need to move the string. Yeah. But as long as like you use a string instead of a C string, you should be fine. Yeah, should be fine. Alright, so next up is std find. But like, what about ranges? Find. Or do we actually need ranges anyway? Probably not. So std find. Oh, contains. Well, that's actually good. Yeah, I haven't programmed in C++ in quite a while. Perfect. Let's go and say shader file name dot contains. Oh yeah, perfect. There we go. Cool. That's way better. Contains dot frag. Perfect. We don't need these braces. Oops, what the heck happened there? Oh yeah. Let's remove that, and there we go. Perfect. Stage contains stage. Cool. And that's basically it. Let's make sure that the shaders are still getting created successfully. And oh, all right, now it needs this to be a std string. Do I like have to make it a std string? Oh yeah, const. Great. Thanks for reminding me. So we could actually accept that. Perfect. And there we go. It works. Lovely. Now let's actually create the pipeline. We're done with that part. Let's create the pipeline. Where's the pipeline? Pipeline. There we go. So here they're actually creating multiple pipelines. One for fill mode fill, one for fill mode line, basically wireframe mode. For now, we're just gonna go with the regular pipeline pretty much. So yeah, SDL create GPU graphics pipeline. Alrighty, let's see. So before we release the shaders, we want to say SDL GPU graphics pipeline. SDL create GPU graphics pipeline. So this creates a pipeline object to be used in the graphics workflow. So of course, as always, you give it the device, and then you give it a create info. So create info, and you're done. Pipeline create info. So let's call this pipeline create info. Why not? Okay, and here we got SDL GPU pipeline create info. The vertex shader, the fragment shader, the primitive topology, it got that wrong apparently. Primitive type, it's called apparently. It got that wrong too. Triangle list. Is there anything else? So the primitive type, the vertex shader, the fragment shader, the fill mode in the raster state. There's also call mode, front face, and so on. Let's go with the fill mode, SDL, GPU, fill mode fill. You could set the call mode to later on, but for now, let's just keep it as it is. And we're gonna need a target info, which gonna have color targets. Okay, interesting. So we're gonna have a vector of color targets. We could probably use an array, but I'd rather have that deduction on. It must be because the AI has been autocomplete SDL2 for so long it's not used to the macros being changed. Yeah, true. Color target. Okay, color target. So SDL GPU, color target info, color target. GPU color target. Actually, no, it's color target description. Color target description. Color target descriptions. So this is the first one, which only gonna contain pretty much a format. There's also blend state there apparently, and for that we're gonna get it from the swap chain. What is it called? Get swap chain texture format, I think. There we go. And you give it a device and a window. And then it would give you the format pretty much. Perfect. Alrighty. I think that's pretty much it now. We just gotta fill it in. And in fact, let's remove this from here and put it up there. And then finally we're gonna set it here. Pipeline create info dot target info. What? Hold on. Target info. And only color targets? No, there's multiple things there. So where is it called? Hold on, target info. What the? Hold on, let me remove this for a second. So it's GPU graphics pipeline target info. There we go. So target info. Target info dot color target descriptions is equal to color target descriptions dot data, and then count is dot size. Well, apparently it's not called that either. Num, yeah, num color targets. Perfect. Now let's set it to the target info there. And it's not really liking that. Okay, there we go. Perfect. Alright, so I think that's basically it. Yeah, I think so. Let's actually try this out. Though I didn't do the error handling just yet. But it doesn't seem to have any problem, at least so far. So what this returns, I think, yeah, null. Okay, so if not pipeline, then couldn't create GPU graphics pipeline. Let's make sure that this is being created. Perfect. There's no errors at least, so that's cool. Alright, so the next is we gotta tell our render pass to use that pipeline, or we gotta bind that pipeline to our render pass so we can start using it to draw stuff. So SDL GPU bind, well, yeah, bind GPU. Well, bind GPU graphics pipeline. I haven't got used to the new GPU API naming conventions, but I guess I'll do with time. So we got here the pipeline. Perfect. Now we bound the graphics pipeline, we could actually use it to draw stuff. Let's draw 3 vertices, which are basically hard-coded into the shaders that we're using. So SDL GPU draw, or draw GPU primitives. So draw data using bound graphics states. So here, of course, the render pass. 3 vertices starting, well, and 1 instance starting from 0 in both the instance and the vertex. Perfect. That should probably do the job. Let's see. Do we have a triangle just yet? Or did I forget something? And there we go. We have a triangle. Perfect. It's that simple. So, yeah. Alrighty, well, let's just make this 0.1 in the red, 0.1 in the green, 0.1 in the blue, and there we go. And yeah, it works. Perfecto. So this is exactly what I've made by myself. So now we're actually stepping into the area that I haven't explored just yet. This is quite interesting. Okay, so let's go to the next step. The next step, we probably want to try to do maybe a basic vertex buffer, so we don't have like hard-coded vertices anymore. And for that, we're going to be using a position color vertex shader that exists in the content folder already. So let's see here. Let's change the shader basically. Let's change the fragment shader to solid color.frag. Well, it's already there. Perfect. So we only changed the vertex shader apparently. Alrighty, let's see what I have changed now. Okay, so the vertex input state apparently. Number of vertex buffers 1. And vertex buffer descriptions, okay. So of course we changed the pipeline to add that information, and then of course we created GPU buffer. Size of position color vertex times 3. To get data into the vertex buffer, I have to use a transfer buffer. Well, basically an employed buffer. Interesting. We map the GPU transfer buffer. Then we map it after we write the data. Then we apply the transfer data to the vertex buffer. So I know Vulkan, so this is like very simple to understand for me, but I know for sure that a lot of beginners right now are like going, what the heck is going on? Oh man. Begin GPU copy pass, apply to GPU buffer, and GPU copy pass. Interesting stuff. Okay, let's go. First of all, where's the data? Where's the data? Let's see. Position color vertex. Oh, we're actually writing the data here apparently. But there is a struct though called position color vertex. What is that? Oh, I think it's in the common.h file apparently. And why? There we go. Okay. So common.h file. Whoops. Position vertex. Okay, so here we go. Interesting. So they're basically define their own matrices crap and stuff like that, which we're not gonna do. We're gonna add GLM. GLM C++ to our CMake. It should be very simple to add, really. So, by the way, we don't have MGY here, so we could just remove this stuff, I think. There we go. Now let's add GLM here. It's actually very simple. We're just gonna add that, and then, so of course this thing is coming from here, g-truce GLM. And then I'm gonna copy this tag, which is the latest commit, and then I'm just gonna append libs GLM, and that's basically it. How I'm gonna add GLM. Simple as that. Now let's regenerate our CMake. Run this up. Couldn't be any easier in C++. Oh boy. There we go, it's building it. But apparently there's an error for whatever reason. Cannot open file glm.lib. Huh. Why? Well, this is interesting. Oh, it's called GLM. This is the actual target. Alright, let's try now. That's strange. Cannot open file. Let's try to do it directly here and see what's up. There's also header only, but if possible I want this one to work. I don't understand why it doesn't. Is there any extra things that I forgot about in terms of building this? Man, doesn't seem like. Doesn't really seem like. Alright, that's strange. Well, it did say something about some variable. Dbuild shared libs equal to on. Man, let's just go with header only, please. And see what's gonna happen there. And let's just actually use that here. It's kind of strange why this didn't work. What do you expect from CMake? But anyways, let's see now. Now I need to figure out how do you use that header only. So build finished, perfect. And oh, I'm getting validation errors of Vulkan. Interesting. There we go. So because I have like the Vulkan SDK, I think, or maybe it's automatic using SDL. I'm not sure. Does not have a location 0, but Vertex shader as an input. Oh yeah, makes sense. Alright, let's see. Alright, so how do you use this header only thing? Bro, what? Okay, let's just do this. Hold on. Include GLM slash glm.hpp. And let's go inside of this. Is there like an implementation or something? Huh. I mean, let's just try this out and see for ourselves. And everything seems fine there, okay. Now let's actually try to use this. Okay, fine. Let's go ahead and do this. Da, da, da. Basic triangle.c. Da, da, da. Where is it? Well, not basic triangle, basic vertex buffer. Okay, so we need this vertex input state here. Let's add it to the pipeline, sure. So where's the pipeline? Here we go. Oh, vertex input state. And here we're gonna need SDL GPU vertex input state. Vertex input state. Here we're gonna add it. Now let's see what we got here. Number of vertex attributes. So we're gonna have a vector apparently of vertex attributes. And a vector of what else? And descriptions, vertex buffer descriptions. Or should I say just vertex buffers? Vertex buffer descriptions, there we go. So basically for this one it would be vertex attribute, and for this one it would be an SDL GPU vertex buffer description. There we go. Okay, cool. Now vertex attributes dot push, or I don't think, let's just go with pushback, why not? And SDL GPU vertex attribute. Alright, so buffer slot 0, format, location, and offset. Okay. Location 0, buffer slot 0, and the format is the GPU vertex element format float 3, I think, and 0 for the offset here. There we go. Then we could probably say in place black instead, and then we're not gonna need this. I could just do this. Alrighty. Yeah, it's float 3, perfect. And then U byte for norm.
Okay, let's see what we got here. Vertex in place back. So the location is 1. And the buffer slot is 0. And then the other one is u/4 norm. Offset is size of float times 3. Size of float times 3. Okay. Alright. For the vertex buffers, we're only gonna have 1. Fields are in different order. Huh? What do you mean? Vertex input states, and by the way, I actually haven't added them. So vertex attributes is equal to that. This one it missed it because it's inconsistent, unfortunately. So the AI didn't pick up on that. Alright, cool. Next up is we need the vertex buffer descriptions. So the first thing first is the slot, which is probably 0. Yeah, and then what? The pitch, then the input rate. So the pitch is size of position color vertex. So size of GLM vec3. And I think that's float, right? If I remember. Yeah, it is. Perfect. That's the pitch, and now the input rate. What the heck? Is the LGP vertex input rate? Is the LGP vertex input rate vertex? Cool. And then the instance step rate, which is 0. And we're done. So 1 vertex buffer. Cool. Now what? We probably gotta create the buffer after that. Yeah. Can we actually create a vector right now, or should I say maybe? Yeah, vector. Or can I actually just make them directly here though? Interesting. Let's not overcomplicate stuff. Let's just get working. So here we're gonna have vertices, which is gonna be a vector of GLM vec 3 vertices. Hold on. Though it's not just vec3s, it's gonna have like flow 3 and u/4 norm with an offset. Oh yeah, I see. So we're actually gonna need a struct though for this. Struct vertex. So we're gonna need a vec3 position and the vec4 color. Though that one is using u/4 norm, which is interesting. I mean, what is that position color vertex again? Let's see. Yeah, as you can see, u_8. I'm not sure if that's part. And for the color, it's like and well, yeah, there is. Cool, perfect. Which is cool. Alright, so we got the struct vertex now. Great. Now let's actually say cd. Yeah, vector, vertex, vertices, and we got the positions and the colors. Perfection. Alright, now what? Let's go back to that thing. So now we're gonna create the GPU buffer, though we're gonna need a GPU buffer create info. So like SDL GPU buffer create info, buffer create info, yeah. Size of vertices, yep. Usage, yep. And data. Though no, we don't need data here. In fact, data is not that easy to set. We gotta apply the ease in the buffer. Did you mean dot size? Well, not really. But this is not really what I wanted either. Oops, dot size. Times size of vertex. There we go. I wonder if there's like a function to do this. I mean, this is very simple, but cd function to get a number. Meh, it's the same exact thing. Never mind. Alright, so after this, we need a transfer buffer apparently. So, SDL GPU buffer create info, transfer buffer create info. And for that one, it's called upload, right? What? Oh, transfer buffer usage apparently. So there's upload and doloid. So let's go with upload here. Perfect. And now we're just gonna create it basically. So so let's actually create a buffer here first. So vertex buffer, SDL GPU buffer. Well, probably maybe vertex buffer. No, what the heck? There we go. SDL create GPU buffer. Okay, perfect. Now this could fail, right? Yep, it could, of course. And now here, let's do the same thing with the transfer buffer. Okay, perfect. Though here, though, we could have easily just, but no, we gotta add props and so on. Well, never mind. Never mind. Alright, so now we have both. We have to basically write the data. Well, first of all, we have to map the buffer into the CPU memory, so we could write to it. Alrighty. and then it would give me back a pointer. Interesting. All right. I could make use of a span here. I think I could make use of a span. Or can I? Problem with a span is that well, let's just try it out. Let's just try it out. So std span. Transfer buffer span. Map GPU transfer buffer. So of course we're gonna need a device. Transfer buffer, and then bool cycle. Probably just say false for now. I'm not using any cycling crap right now, I think. Isn't it? Yes, it is. Okay, so what's up here? Cannot converge. Oh. That's strange. Hold on. Oh, so create GPU transfer buffer. Interesting. So here we're gonna need a device. And apparently have its own thing. Which is strange. Why? I could, by the way, just say auto here, really. And call it a day. Yeah. I'm not sure why they have separate functions for both of these. They're pretty much the same. But whichever. Anyways. So here argument deduction failed. Let's see. So the type would be a vertex. And I think I probably want to give it the size too, which is basically the vertex size, or isn't it? And that doesn't seem to work at all, apparently. Or maybe it's the opposite, like the length and then pointer. What the heck? Let's try that. It's near 2 a.m. for me. Otaku, I'm off to sleep. Have fun with the stream. Goodbye, Robert. Thank you for coming in. Goodbye. What the heck is happening here? How can I make a span out of a pointer and the length? It's really that simple, man. But then why this doesn't work? It's interesting. Alright, let's say auto PTR is this. Oh. So I guess this is the way it's done. So first I get the pointer and I make sure it is valid. Then I make a span out of it. Perfect. Static cast. Do I really need a static cast? I think so, but it's probably what I was missing beforehand. Yeah, apparently. So I just needed that static cast to a vertex pointer, which is cool. Though I could have probably just casted that one instead directly. No? There we go. And I don't know if I even need that anymore. Yeah, pretty much. That's cool. And I could probably just say this instead. There we go. That's pretty sick. Instead of pointer, I should probably rename it to something better. Transfer buffer data, I guess. Data PTR. Now this is the transfer buffer data. STD copy, so we're gonna copy that stuff into the use algorithm STD range. Okay, so we're gonna copy the vertices to the transfer buffer data span that we created here. And yeah, that should be pretty much it for that one. And then finally we map that. So SDL in map. In map. So here we need the device and then the transfer buffer. Because we're done with the well, not the upload, but like writing to the buffer. Then we don't need access to it anymore, so we could just in-map it essentially. So yeah, pretty much. Now we're gonna upload that to GPU buffer. Oh, but before that, of course, we need a GPU command buffer. We begin the GPU copy pass. Interesting. Is everything okay so far, though? Is everything okay so far? Yeah, seems fine. Other than, of course, the drawing stuff, because it's not having the buffer just yet. Which is understandable, but other than that, at least we're not crashing. So right now we're gonna need to make an upload command buffer. So command buffer, which we can add to some or record to some copy commands. So SDL acquire command buffer. So now what? I gotta begin a GPU copy pass. GPU copy pass. And now what? SDL upload to GPU buffer. So here we got the copy pass, the transfer buffer location. Really, where's that comes from? Oh, it's that. Okay. So we give a transfer buffer and an offset. I think I could just do it here, really. Transfer buffer, comma 0, probably. and then the destination, which is a buffer. Then offset. Huh. I'm not sure if this is correct. Well, let's just remove this and say, well, it's actually supposed to be a reference. That's why it didn't work, apparently. That's really sucks. We don't have those, you know, designated initializers like these in C++, unfortunately. Which really sucks. I hate it. But anyways. So here is the GPU transfer buffer location. And yeah. Is there anything else? I don't think so. Yeah, that's basically it. Now we also need SDL GPU transfer. GPU buffer region, apparently. Right. Oh yeah, and finally the size. Now I could just go ahead and say transfer buffer location, or like source and destination. So this is basically source and this is destination. And cycle false. And of course here we need to give it these addresses, and there we go. And finally we enter GPU copy pass and submit the GPU command buffer and release GPU transfer buffer IC. And we don't need the transfer buffer after this, after the upload is done. So we could give it the device and then a transfer buffer. And I do think it probably can fail, right? Or no? No, it's void actually, which is interesting. So, okay. And yeah, that's basically it. Then finally we show the window. Yep, pretty much. Now the other thing is that we gotta actually use this stuff now. So basically what we're doing here is that we're having a command buffer, or like a transfer command buffer, that is visible to the CPU, or should I say even better, the system memory, the RAM. Right, and we're basically copying data from that transfer buffer, or should I say we're copying data from our program to that transfer buffer, and then using command like using the GPU, we're copying data from that transfer buffer to the vertex buffer that is in the VRAM, right? And that's basically how it's working here. That's why we need all this stuff. So yeah, all right, what's happening here? Alrighty, let's see what we got. So bind graphics pipeline, and before we draw, let's make sure to bind the vertex buffers. Bind GPU vertex buffers. So this takes a render pass, of course, and it takes a first slot, which is probably 0 here, and then let's see what's going on here. Yeah, 0 for the slot, and here we got buffer and an offset. And well, that wouldn't work either. This really sucks, but oh, number of bindings, I see. So here we could say bindings.data and bindings.size here. And here we could go with cd vector. There we go. Perfect. Perfect. Alright. I think that's basically it, maybe, for the GPU buffer stuff. And it's not working. Well, that's gonna be interesting. Let's see. Why wouldn't it though? Can we call that transfer command buffer, please? Let's see. Let's call this transfer command buffer just so we don't have any problems there. Submit GPU command buffer. I think we need RenderDoc here, honestly, so I could have a little bit more information here. Deloitte. Because there's just a lot of things that could go wrong here. So the best way is to get RenderDoc or any other debugger, graphics debugger, and see what the heck is going on. Next, accept, next. Find typical install. Yes. Finish. Let's launch RenderDoc. Let's grab the path of that executable. There we go. Okay, how do I copy path? Absolute path. Executable path. Working directory there. Or isn't it? Yeah. And let's try to launch this. Okay, let's capture a frame here. And let's see what the heck is going on here. So we're having a color pass. We're drawing 3. Okay, and we're binding a vertex buffer here. We're binding some descriptor sets. Okay, I don't remember how the heck do you find out. Okay. Cool. Okay, so this is the data of this buffer. Why the heck this is in hex though? Can't you just show me the thing? That's strange. Oh, there we go. Okay, cool. Okay, so something interesting happening here. So this is the vertex input and this is the vertex output, which are probably this, yeah, pretty much the same exact thing. So that's, we could ignore that. Now the real deal here is okay. So 0, 0.5, 0, which is correct here. -0.5 minus 0.50. Right. And no, something terribly wrong here. Oh, hold on a second. What the? Freak. Probably this is a problem. What? Oh, I see. Well, where's that transfer command buffer? Bruh. There we go. Try out. Okay, it works. Perfect. There we go. So that was interesting. Alrighty. So let's create a rect now instead of a triangle. And that's actually very simple. I'm just gonna comment this out. And then I'm gonna say rect for the AI, and then it would generate rectangle vertices for me, which is basically 4 vertices. I don't think that's enough though, because we don't have an index buffer. Yeah, we need an index buffer. We want to use just 4. Yeah, true. For that, well, what about without I think it would understand now, because we're not using it like an index buffer, so we just gotta give every vertex. Well, actually no, never mind. I forgot that we're not actually taking into account the actual size of the vertices, in fact. Alrighty, size. Perfect. Let's try now. Still. Vertices no size. Let's try this one. Okay, so we're actually drawing two triangles now, but it's not a rect though, unfortunately. Rect. Let's just remove this. Yeah, let's see if the AI could help out here without me having to resort to manually doing it. And there we go. We got our rect. Beautiful. Beautiful, beautiful. Okay, cool. So now we're actually using vertex buffers. Amazing. Now let's add the index buffer too, because why not? So to do that, it's actually very simple. We're just gonna take this, redo it. But first of all, before that, let's just name this appropriately. Let's call this vertex buffer create info. Right, and now we could create an index buffer. But of course we need the indices though, hold on. And yeah, cool. Now let's see what we got here. Perfect. Now we got that out of the way. And oh, this should be that. And yeah, there we go. Now we need to also copy that over. And well, for this one, I'm not sure about the alignment requirements, but I would just guess I could do something like this for now. So vertex buffer size plus the index buffer size in the transfer buffer, so we don't need like two of them. And then interesting stuff. Dun dun dun. Interesting. So we shouldn't have the static cast vertex here. Should have it here. Now we need to kind of like offset that. There we go. So we basically offset it by the vertex buffer, create info.size. Of course, it's size in bytes, so it's perfect. And then we copy that over. Perfect. And then what? Source offset 0. Oh, we can't actually set multiple destinations. Well, we could just redo it again, pretty much, yeah. Alright, so basically the destination, well, in fact, even the source should change. So source.offset is vector vertex buffer create info size. Destination buffer is the index buffer, and destination size is that. Then we upload it again. But hold on a second. Should we actually create another one because this is an address? Well, it depends. Does it actually like copy that over, or what exactly is happening? I guess the best way to find out is just to create another one and call it a day. So I'm gonna recreate these, and yeah, better be safe than sorry, I guess. And yeah, pretty much. But well, no, that wouldn't work. I see. Ba-ba-ba. I'm just trying to copy this over. Well, you know what? Just try this anyways. Unknown size. I see, makes sense. Oh my god, no. This is effing up my brain. You know what? To keep things very simple, I'm not gonna do this kind of crap, at least not now. I'm just gonna create a separate transfer buffer for this. Because this is wild. It would have been more efficient in one buffer, but man, just very confusing. I think so far here we actually had a working product, right? Let's see. There we go. It is perfect. Alright. Now let's actually create another transfer. Oh, honestly, let's make this whole thing into its own kind of function so we could reuse it pretty much. How are we gonna do that? Let's see. Though, by the way, there was a blog post on that page that I've shared before about cycling data transfer and so on. I haven't actually read it just yet. but it may be useful here. Actually, why the heck am I going crazy here? I could just look for an example, bro. What the heck? Let me see an example. Yeah, true. Kind of played it too smart there. Alright, let's see. Some example. There's this instance index thing here. Let's see how they're gonna handle that. Pretty much. I mean, yeah, they're doing that kind of one transfer buffer here too. Oh man. I'm gonna take a break and then I'm gonna come back.
Okay, back. All right. Let's see what we have here. Pretty much. This is quite interesting. Okay. So the size. All right. First of all, we're gonna need the indices vector, and for that, we're gonna go with UN32. Why not? We could go with UN16, but whatever. Alright, 0, 1, 2, 3, 4, 5. Cool. Now we need another buffer here for the index. Perfect. It's that simple. Now the transfer buffer is where things get really hairy. I mean, so far here it's all good. Now here where stuff goes crazy. Let's see. Position, color, vertex, transfer data. So first we basically the last one there. I see. I guess I understand. Okay, let's see. Okay, so no, we shouldn't map this thing again. That sucks. No. We should like use that data PTR. Bro, you didn't ping when you started streaming. Oh, Marty Flowers, welcome to the live stream. Welcome back. I didn't. I did. I think, yeah. What's up, Marty? Long time. Okay, let's see. Cannot cast from vertex to UN32 via static cast. What? This whole thing should be rewritten. This part. Hold on. Yep, this thing should be rewritten. So I was waiting for the ping with the actual stream. I see. Yeah, it's fine. Alright, so let's see what we got here. So the transfer buffer data PTR should be that. Okay. Then what? No. So like vertex buffer data spam.
So like static cast this into vertex pointer. Or isn't it? Or I think probably we need reinterpret cast here. Maybe that's why this is not working. Yeah, probably. And now we're gonna copy that. And then we're gonna need the index buffer data span. And copy that. I think that's basically what we need there. Cannot rely too much on the AI there. So let's just see, hold on. So the vertex buffer, so here of course we're just getting like a byte, simple byte pointer to the transfer buffer, of course the start of it. Then we're getting a vertex data span, of course starting at the pointer with the size of the vertex buffer create info, which, well, size, huh? Well, isn't that supposed to be in bytes? And yeah, so that's wrong. Yeah, that's wrong, man. That's certainly wrong. Ah, I see. That's interesting. That was close. Alright, indices dot size. Because this is supposed to be the count, not the size in bytes. So that makes sense. And this one is supposed to be in bytes because this data PTR is in bytes. Yeah, that's perfect. That makes all sense. Alright, cool. Now what's next? Now we gotta deal with those transfers pretty much. So let's see how we could deal with those. So we need two calls, of course. Where the offset is this size right here. In fact, maybe even the AI could help me here too. Let's see. So begin GPU copy pass. Let's just comment this out in a second and let's see what's the actual AI would do here. So I don't waste too much time doing this. Okay, cool. Now what about here? Where's that thing? So bind GPU index buffer. Offset is equal to 0. Oh my. Alright, let's see. Let's see what we got here. Bind GPU vertex buffers, first slot bindings, number of bindings, and here bindings offset 0. Yeah, that's fine. And now we just need the bind GPU index buffer too. Okay, sure, why not? Oh, but this one only have ones. Like SDL GPU buffer. Well, binding actually. Buffer binding. index buffer binding, and there we go. I think. No? Has 3 parameters apparently. Oh yeah, the actual argument, I see. Index size 32-bit in this case. And yeah. Now finally, instead of this draw GPU primitives, we should use index primitives instead. But no, that's wrong. Alright, let's see ourselves here what's going on. So the number of indices, indices.size, the number of instances 1, 0, 0, 0, pretty much. If everything went well, this should work, but there is some suspicions I have about some things. Well, it does seem like it's working. At least it does seem like it. If it is really working or not, I don't know. But let's try something here, okay? We're gonna comment this out. And then we're gonna let this thing redo its job. Well, in fact, you know what? Let's remove this whole thing. And this thing. So rect. Yeah, cool. And indices. Perfect. Let's see this, if it works. And it does, which is amazing. So we don't need this anymore. That's perfect. So yeah, it does seem to be working out, which is amazing. Alright, the next thing that I want is to be able to add images. I'm not sure if that's would be easy. I guess we'll find out. But is there even something about that there though? Texture quad, exactly. And we're gonna need the UV attribute, of course. So this would become float 2. We're gonna need to create some samplers. We can actually set the GPU buffer names, apparently. That's cool. That's cool. So basically, this index buffer here, we could say SDL GPU set. Well, set GPU buffer, I think. Device buffer. Well, vertex buffer. Vertex buffer. Same thing with the index buffer. Just for the sake of like the, you know, the debugging thing here, which is cool. Honestly, I enjoy this API very much. It's basically Vulkan but without that, all those like unnecessary details, that crazy boilerplate code. That's amazing. Alright. But certainly my understanding of Vulkan would really help me, because there's no information about like SDL, the new API, and also I could use the Vulkan tools like the debugger and so on, and the other skills that I learned with that. But yeah, pretty much. Anyways, And this one is like a transfer buffer basically. And so maybe there isn't a way to actually set it for transfer buffer, or what exactly is going on there? I mean, I don't see it, and transfer buffer doesn't have the same type for whatever reason, I think. Yeah, I'm not sure why that's the case, why they made like a separate one, but that kind of sucks. But whatever, that's not my business. Alright, so what we need next. So right now, if I actually run this, it should work just the same thing, right? But now if I actually rerun this debugger, capture a frame, and then checked out the color paths, the draw indexed, and you could see that right now we have names here. This is the vertex buffer and this is the index buffer, as you can see. The names that we attributed to them are visible here, which is very useful. But yeah, there we go. That's pretty sick. All right, so. Okay. Now we have create GPU texture. I think the transfer buffer, they have a separate transfer, right? What's going on here? Yeah, buffer transfer buffer and texture transfer buffer, which also makes sense because like images are usually quite large, so they do deserve their own buffer. That's one thing. Second thing is that textures and regular data have varying alignment requirements, at least when it comes to Vulkan, which of course should also apply here. I'm not sure how they're handling the alignment crap, but yeah. Either way, it's not a good... Well, I mean, you can probably, but... Anyways. Oh, I just realized. I just realized what Marty have said. I see. I didn't ping, yeah. Yikes, my bad. Sorry. I just realized what you meant. I thought this ping right here was actually the live stream itself. But whatever, we still have some things to do, at least in the textures stuff. So if anyone is new right now, unfortunately I forgot to ping the live, so we're already in like around 3 hours right now, and we have so far done this rectangle, colored rectangle with SDL3. Right now I'm gonna try to set up textures, hopefully. Yeah, we'll see. So I've not done this just yet off stream, so this is pretty much live. You're the maker of Moon Animator. No, just cutscene plugin in Roblox if you're talking about that, not Moon Animator. And welcome to the live stream, baby. Okay, let's see what we got here. Finally print the instructions, blah blah blah. So how the heck are they loading first of all the image? And where is the image? That's the first thing. Yeah, where is the image? Okay, so there's this image data thing here. Okay, where is that coming from? What? Oh, Lloyd image. They're using BMP, but since we have SDL image set up in our CMake, we could actually even Lloyd even more than BMP. But either way, for now, we're just going to use the images that are here, which is BMP, so it's fine. Ravioli. Okay, sure. Fine. Fine. So SDL surface image data Lloyd image BMP, 4. Sure. And that happened when? After Lloyd in the shaders. Okay, fine. So after, so basically here, okay, before the pipelines, sure. So what did they call the image data? Okay, SDL surface image data, SDL Lloyd BMP. Actually, no, Lloyd image is basically like actually in common.c, like it's a utility function, I think. Lloyd image. Okay, there we go. Apparently. So it takes a file name and the ZAR channels, and then it does all this crap. Interesting. Oh, convert surface into some specific format. I see. So they're basically unifying the formats of the thing for rendering. I'm just gonna copy that function. Honestly, I'm gonna use it myself. Okay, let's see what we got here. First of all, all of these could become null PTR. And what's next? Declaration and assignment could be joined. I guess, sure. For this one, we could just use, you know, okay, so full path, cd string, full path is equal to that. Now here dot c stir. Okay, here we wanted to say throw SDL exception, so if not result, then throw SDL exception. If desired channels is equal to 4, then do this, otherwise throw an exception once again. But like, is there, hold on. No, it's fine, never mind. Okay. And what's going on here? Destroy surface. Result is equal to next. Okay, that should work. Yep, that should work. Alright, so right now I could just say Lloyd image. And here I'm gonna need the image file name, and in this case let's go back to the example that we were in. There we go, ravioli.bmp, 4. And there we go. Now, so far here, does this work? Are we loading the image in the first place? I mean, doesn't seem there is any problem there. Cool. Now we gotta change that attribute first of all. We gotta remove that color. So let's go to the vertex here. Instead of this, we're gonna go with Vic2 UV. And then where we're doing the float stuff, okay, so the attribute here, we're gonna say float2 size of, well, yeah, GLM Vic3, perfect. And what else? Though we could probably automate, well, not automate, but like, I remember there's like an offset off function, yeah. There we go, perfect. And just to keep things consistent, we could even do it here, although I know this one would be 0. But yeah, it's also quite readable, so I know that this is the position, this is the UV, and so on. Yep, pretty much, that's perfect. Okay, this is reminding me of the OpenGL days. Oh, whichever. Alright, so what's next? Now here we can of course change this stuff a bit. std vector, because we don't have colors anymore, we have UV. So let's leave the AI do its job, and we're good to go. We're good to go. Okay, cool. And now what we gotta do? We should already have like, but no, I think I'm probably gonna need to like change the, oh yeah, I surely gotta change the shaders. So the textured quad, which shaders are used? Textured quad vert and .frag. Okay, cool. Lovely. So I don't need to deal with that. Textured quad .vert and textured quad .frag. Perfect. Let's see. It should give a warning or something. Because we, yeah, it actually have crashed. Oh, which makes sense because we don't have any like texture bound. Alright. So let's continue with our job here. Float2, vertex. Okay, so we're gonna need these samplers pretty much. So nearest or linear? I think I'm gonna go with linear probably. And clamp should be okay, I think. So let's go with linear clamp. And let's go to where this is being made after the shader stuff. let's see, release GPU shader. So apparently here, for whichever reason, auto sampler, and here instead of context device, it's basically device. Oh, yeah, this wouldn't work. So let's just say sampler create info, really. Call it a day. And now I'm just gonna comment this out and do this. Perfect. Now I can remove this and we're good to go. Now we have a sampler. Perfect. Next is you gotta create a GPU texture. And of course for that we need a texture create info. So auto texture, well, yeah, texture create info. Oops. I mean, so type. What? Oh, I see. Perfect. What about the format? RG. Well, let's just copy this dude. And we're good to go. So we need the width and the height from the image data. And the height from there, depth 1, because, well, do we actually have depth? No, we have layer count or depth. Okay. Layer count or depth is equal to 1, and then the number of levels is equal to 1, pretty much. Then usage. What's the usage? Texture usage sampler. Color target, I see. That's pretty much it, I think, for that one. And I could even also give it, but hold on, I need to first of all create it though. So auto texture, SDL, create GPU texture, and then if not texture, then throw an exception, and then set GPU texture name. We could call it ravioli.bmp, just like the file name itself. Why not? And then here we need to set up some buffer data. So I think the texture data should have its own GPU transfer buffer apparently. Okay. SDL GPU transfer buffer info, create info, yeah. Well, texture transfer buffer create info. Size is image data pitch times height. Is that true? Well, here it's actually saying image data W times, or width times height times 4. Here it's saying pitch times height. I think it should probably be the exact same thing, if not better. Yeah, sure. Okay, cool. Set the name, because why not? And then, well, oh, I just remembered that it's not possible for transfer buffers for whatever reason. Okay. Now, let's see if the AI does its job here. Okay, cool. Though that transfer stuff, I'm gonna bring it from here to the place where I do the transfers. It's becoming a spaghetti here, but it should work, I think. Alright. So right now we copied that data there. Now what we're gonna need is to copy that buffer. So before ending the GPU copy pass here, you gotta use the texture transfer buffer. Whoa. Whoa, whoa, whoa. I guess .w maybe? I see. Well, that was close. It's just that it's supposed to be GPU texture transfer info instead. So where's the source here again? It's here. So then that means I gotta actually redo this. No. It's like this is source, I guess. I'm very confused. Hold on. Go back. So this, what it needs, GPU texture transfer info, which is correct. So what the heck? What's wrong with you? Oh, transfer buffer, I see. Right. Offset. Oh, hold on. Is that really even what I need here? Applied to GPU texture. Yeah. I guess we'll find out. So let's actually see what's happening here. Apply to GPU texture, there we go. Offset 0. And that's basically it for that one. And finally the region. So GPU texture region. And then the D, or the depth. So WHD. And since these are zeros, we don't need them. Same thing with this one, probably. Well, yes, I guess. name. All right. And then I can use that, I guess. There we go. All right, perfect. Now how do I use that image, or like how do I attach it to the oh my god, I gotta update that crap. Interesting. Oh, okay. No, well, we'll see. Alright, where's that happens? Bind GPU fragment samplers. SDL, bind GPU fragmented samplers. Okay. When they did that? Before the primitive stuff, okay. Probably, yeah, the render pass. Now here we need the first slot. First slot is 0. Now here we got texture, sampler bindings. Okay. For that we're gonna go with a CD vector. Oops. But no, it's not. So it's a GP texture sampler binding. And now you can do this and then do this and this. Okay. That's wild. Okay, cool. Is that all we need? Maybe. Oopsies. Apparently. So something missing in the Vulkan layout, which means that I have some problem with the pipeline setup. Okay. Pipeline setup. Well, the pipeline creation doesn't seem to really have anything that interesting, I guess. Which is strange. But are we at least uploading that to the VRAM, like successfully? Let's see. But I'm not sure if it's probably gonna crash on me. Yeah, unfortunately. Can we maybe try to do queue capture? Nah, because it crashes. Yikes. Where the heck is that sampler being used? Should be somehow. But like, how the heck am I supposed to add it to the layout then? That's interesting. Can we try again? Okay, let me see right now what's going on here. Yeah, but like, how the heck do I set it? Okay, let me see. So the graphics pipeline have this pipeline create info. Vertex shader, of course, not. Okay. But how am I supposed to do the layout stuff? That's strange. Yeah, there's literally nothing about textures here. Oh my god, I'm stupid. Really stupid. Lloyd shader. Okay, let me see. Because like in my mind, the layout, the pipeline layout is not part of a shader module in Vulkan. It's like it's part of the actual pipeline. Well, not exactly, but well, whatever. Anyways, so I think here sampler count 1, right? Is that was the problem all the time, like all this time? I mean, yeah, we're getting something. That's cool. So it works, I guess. Now we need some more interesting image. Some more interesting image. Well, we wouldn't go too far. I'm just gonna take a capture here And like I'm just gonna copy this file, gonna open this grab explorer, and then I'm gonna paste it into the images here. Oh, well, I'm gonna copy this path, save, and let's just call this screenshot real quick. So it's going to be a PNG file because all the other ones aren't really PNGs. And since I have SDL image set up, I could probably make use of that, at least in theory. So we'll see. That's what we're going to try now. Alright, cool. Where that Lloyd BMP crap is happening here. Okay, cool. So SDL Lloyd. Okay, how the heck do you use that SDL image? Examples, show image, Lloyd, EMG Lloyd, okay. Of course, in SDL image file. Perfect. Now this of course also gives us an SDL surface. Okay, let's see. Lloyd image directly to an SDL texture for use by the GPU without using. Oh, but that's for the 2D rendering API, not. Okay, cool. So I think this should really solve the problem, and then instead of ravioli or whatever that's called, you could probably just screenshot.png ravioli here, screenshot.png, and I mean in theory they should probably work. And boom, it doesn't. Let's see why. Why it doesn't want to. Okay. So we got some sort of an exception here, but like a known, which sucks. Oh, here we go. Okay, never mind. So couldn't Lloyd the image. For whichever reason AMG Lloyd is giving me null. AMG Lloyd giving me null. Okay, why would it? Or null on error. Okay. Well, one thing for sure that I should do is to wrap this main function in a try statement. Or for now, at least, just temporarily, let's just do it here. I don't even remember how the heck do you do this. Okay, like this, right? So try and catch. Man, just like print the error message too simply. Where the heck that gone? There we go. Oh my god, I hate this. Okay. Couldn't open. The system cannot find. Alright. Ah, I see why. I see why. So let's just remove that stuff that we've done right now, because I know exactly why that's a problem. Because right now, unfortunately, with how it's copying the assets is done, I need to actually reload my CMake projects so we can recopy this thing. It sucks. Or I could just add some functions here, whatever. Let's see. So we could recopy the thing. Well, whatever, just do this and this. Now it should work because it's gonna copy the folder again. And let's go, it works. There we go. This is our PNG image into the rectangle. Perfect. And if we actually even try this in the debugger, launch, could capture a frame, and there we go. Now, where is the inputs here? Oh, there we go. Now, as you can see, this is our texture, looking perfect. Amazing. There we go. So, yeah, that was a lot of fun. I wonder if there is anything that we would want to do before we end the stream. Let's see the other examples. Well, not SDL image. Let's see the other examples of. Oh, where the heck? There we go. All right, let's see. Instance indexed. We could do instances, but that's not a big deal. Tone mapping would be interesting. It would need like compute and so on. MSAA would also be interesting. You would need a separate attachment. Window resize. Is there like some specific stuff to do for window resizing? That would be wild. Huh. Let me see. I'm not sure what it's talking about here. I'm not entirely sure. Is there like a description for this example? Apparently not either. What is this tone mapping? Hold on, let's see. Man, the tone mapping is a bit advanced. Maybe some another day. But there we go, the compute pipeline stuff. Alright, perfect. Anything else? Latency. Draw indirect, generate maps. Hey, I think I'm gonna stop the stream here. We got a textured quad. We have actually already done quite a few things there. Loaded images, you know, dealt with buffers and so on. Yeah, I'm gonna actually publish this though. There isn't a lot of, well, in fact, I don't think you'll find any C++ code base that uses SDL3 at the time of recording, like SDL3 GPU. But at least not a public one, but yeah. Alright, so let me see. Changes. Do I have... no, I probably don't. I need to git init. Well, not git init. What the heck I'm saying? Git ignore. Build directory. Ignore that. And yeah, inversion files. May I just add all of them? What about the source code though? Add VCS. That's strange. Well, I guess I'll figure it out off camera, and then I'm gonna put the link down in the comments or the description. So yeah, that was it guys for this video. Oh well, this live stream. We have explored how to make oh well, hold on a second. This is actually flipped. Hold on, this is actually flipped. Wait, let me solve this problem first, hopefully. Then we could go one way, probably the easiest is to probably just flip the UV, I guess. Where is that thing? There we go. Let's try. Yeah, right now it works perfectly. There we go. Cool. So yeah, that was it guys for this stream. Thank you all for coming in and see you later. Goodbye everyone.